The question over here is the correct IUPAC name of the following structure is. Very simple, easy peasy, lemon squeezy question. Why so? Because it's a very simple compound given to us to name for IUPAC nomenclature. So basically, first of all, without seeing the options, let's actually write the correct IUPAC name of this particular structure. Over here, we are given with a functional group OH, and yeah, there are two substituents attached to this particular benzene ring basically. Fine. Now, OH group is a functional group. It's been given priority over the substituents. With substituents, the methyl substituents. Okay. Moreover, in this particular question, the benzene ring is actually considered to be as the parent chain. So, we'll be start numbering from that carbon atom to which the functional group OH is attached. So, it's 1, it's 2, it's 3, 4, 5 and 6. You can do the numbering from this side also because you will get the same positions of the substituents, okay, which are 2, 6 basically. So if I just name this IUPAC, if I just name this particular compound and give its correct IUPAC name, it will be basically, it's 2, 6. Why? Because at 2 positions, at 2nd and 6th position, we have dimethyl. At 2nd and 6th position, we are having the methyl substituent attached. So it is basically 2, 6 dimethyl. Okay. And what else I'm going to do over here? We can write it as benzenol. Okay. You can also write it as 2, 6 dimethyl phenol also. Or you can also write it as 2, 6 dimethyl phenol, because this particular compound is basically known as phenol. That's why. Okay. So let's see the options given to us in the question. So over here it's 1, 3 dimethyl benzenol. Absolutely wrong. 2, 6 dimethyl benzenol. Absolutely right. 1 hydroxy. 2, 6 dimethyl benzene. See, it's why we are taking hydroxy as a prefix. It has to be used as a suffix because it's actually the functional group. Priority has been given to the functional group and it will be used as suffix, not prefix. So absolutely wrong. 1 hydroxy, 1, 3 dimethyl benzene, wrong. It's only option number B, the right answer to this particular question. At 87 degrees Celsius. So 87 degrees Celsius means equals to 87 plus 273, which is equals to 360 Kelvin. Initially, we should do these particular conversions. It becomes easy for us, is it? Yeah, of course. So the following equilibrium is established, and that equilibrium is H2 in the gaseous state plus sulfur in the solid state is in equilibrium with H2S in the gaseous state, wherein the value of Kc equilibrium constant is given to us as 7 × 10⁻². Now what the question is asking us? If they are saying if we are having 0.5 mole of hydrogen and 1 mole of sulfur, okay, if they are heated at 87 degrees Celsius in 1 liter vessel, what will be the partial pressure of H2S at equilibrium? You have to calculate the partial pressure of H2S at equilibrium. Very simple to calculate. Easy peasy lemon squeezy question. Why so? Because see, I'm actually going to do and solve this particular question for you guys. So basically, if I just straight away say that initially, since we were having the number of moles of hydrogen as 0.5 and the number of moles for sulfur as 1 mole. So at equilibrium, if I just talk about, so what will be the number of moles left of H2 gas? Suppose X moles of H2S has been formed at equilibrium. Absolutely right. Okay. So it means 0.50 minus X moles of hydrogen will be left at equilibrium and 1.0 minus X moles of sulfur will be left at equilibrium. Now if I just talk about Kc, okay, I want to calculate equilibrium constant. It is equals to the product concentration H2S divided by reactant concentration H2. They are in the gaseous state, so I'm taking it. But sulfur is in the solid state and for it the concentration term is actually equals to 1. Activity coefficient value for the things in solid, they are actually considered to be 1. So we ignore it. Okay, no issues. So it is equals to 7 × 10⁻². Absolutely fine. So it is x upon 0.5 minus x, okay, equals to 7 into 10 raised to power minus 2. Now what you have to do? Obviously, what do you have to do? You have to just cross multiply them and get your answers. So basically, it's x equals to 5 by 10 multiplied by 7 into 10 raised to power minus 2 minus 0.07x. So it is x plus 0.07x, fine, which will be equal to 35 into 10 raised to power minus 3. It becomes 1.07x equals to 35 into 10 raised to power minus 3. 10 raised to power minus 3. So x is equals to 35 into 10 raised to power minus 3 divided by what? It will be 1.07. So when you will calculate this particular thing, you'll get the answer as 0.0327. The value of x is actually 0.0327, number of moles of H2S in the gaseous state. Now if I want to calculate out the partial pressure of H2S gas, so it will be actually equals to number of moles of H2S gas, fine, divided by V volume multiplied by R into T, because we know that pressure is equals to N by V into R into T. Substitute the values. So over here, its partial pressure of H2S gas equals to number of moles of H2S gas, which is 0.0327, divided by volume V, which is equals to 1 liter. So we'll not take it. Okay, obviously, just take it. Hardly matters. No use because it's 1. So multiplied by R, we are going to take the value of R in terms of liter atmosphere. So it will be 0.0821. Okay, liter atmosphere per Kelvin per mole, because this is in moles. This is liter. So it's liter atmosphere per mole per Kelvin multiplied by 360 Kelvin. Kelvin cancels with Kelvin, mole cancels with mole, liter cancels with liter. We are left with ATM. When you just multiply all these things, just take the approximation. It's 0.03. Okay, multiplied by 0.082. Or you can say take 0.08. I'm taking the approximation. Multiplied by 360. Now you have to solve it, and yeah, you will get the answer as 0.966 ATM. Okay, the approximate answer basically. So we'll just look for the partial pressure. So it's option number A, 0.966 ATM, the right answer to this particular question. The question over here is basically what? There is a solution, and that solution consists of a mixture of 0.05 molar NaCl and 0.05 molar NaI, sodium chloride and sodium iodide. So there is a solution having a mixture of NaCl and NaI having the same concentration, 0.05 of both. The concentration of iodide ion in the solution, the concentration of iodide ion, that means this. Okay, in the solution when AgCl just start precipitating is equal to. So we have to actually find out the concentration of iodide ion in the solution at which particular stage when AgCl just precipitate out. So the precipitation of AgCl just happens up, and we need to find out the concentration of iodide ion at that particular stage. Are you getting that point? Okay. Wherein we are over here given with the solubility product value of AgCl, which is 1 into 10 raised to power minus 10 molar square, whereas the solubility product value KSP, okay, of AgI has been given to us as 4 into 10 raised to minus 16. So from this particular data, this is actually clear that KSP value of AgCl is greater than KSP value of AgI. That means solubility product of AgCl is greater than solubility product of AgI. Now, remember, lesser is the solubility product, more will be the precipitation, more precipitation. From this particular thing, what we are actually analyzing and judging is, since the solubility product of AgCl is greater than the solubility product of AgI, solubility product of AgI is less, which means AgI is going to precipitate out first. AgI is going to precipitate out first. So there is a mixture, okay, I mean to say solution mixture having NaCl and NaI. To this solution we are adding obviously silver solution, okay. And what happens, as in when we just add the silver solution to it, what happens, it's AgI which precipitate out first, okay. Okay, now from this particular theory, what I actually analyze is that since AgI precipitate out first, which means it is going to consume some amount of this particular concentration, because NaI plus Ag positive, NaI plus when NaI reacts with silver solution, it's AgI which is going to precipitate out. Okay, that means some amount of this particular concentration of NaI is being consumed to precipitate as AgI. Is it or not? Yes, of course. This is what I want to make you understand. Okay, this particular point is clear. Okay, now this is a thing that AgI is going to precipitate out first. So we'll be actually calculating out the concentration of Ag positive. We want to know the concentration of Ag positive, okay, to precipitate out as AgCl. What will be the concentration of Ag positive ion required to precipitate as AgCl? I repeat the statement again. We want to find out the concentration of Ag positive required to precipitate as AgCl. We know that AgI has been precipitated out already. Reason being, I have just told you. Is it clear? Okay. So Ag positive, concentration of Ag positive, okay, required to precipitate as AgCl. So Ag positive, concentration of Ag positive to precipitate, okay, to precipitate out as AgCl. What will be the concentration of Ag positive so that the precipitate of AgCl is going to form, just start to form. So it will be Ksp of AgCl divided by what? The molar concentration basically of NaCl, because this is NaCl, and when we'll pour the silver solution, it will actually react with NaCl to form AgCl. Okay, so we'll be using this particular concentration. That's cool. So it will be 0.0, it's 0.05 molar, 0.05 molar. So it's 1 into 10, 1 into, wait a minute, it's 1 into 10 raised to power minus 10. 10 raised to power minus 10 molar square upon 0.05 molar. When you will calculate this answer, you will get the answer as 2 into 10 raised to power minus 9 molar. That means at this concentration of Ag positive ion, this is the required concentration of Ag positive ion to precipitate out as AgCl. At this concentration of Ag positive ion, AgCl is going to precipitate out. When in the solution, this particular concentration will get, AgCl is going to precipitate out. I repeat myself, this is the concentration required of Ag positive ion to precipitate out as AgCl. I'm making the things very, very clear. Okay. Now, at this particular stage, we want to find out the concentration of iodide ion. Because we want to find out the concentration of iodide ion when AgCl just start to precipitate. At this concentration, AgCl just start to precipitate. Which means the concentration of iodide ion at this stage, which stage I'm talking about, this stage, it will be equal to Ksp of AgI, okay, divided by the Ag positive concentration. So it will be, it's 4 into 10 raised to power minus 16 molar square, 4 into 10 raised to power minus 16 molar square divided by concentration of Ag positive, which is 2 into 10 raised to power minus 9 molar. And when you'll just calculate this particular thing out, you'll get the answer as 2 into 10 raised to power minus 7 molar. This is the right answer. So the concentration of iodide ion when AgCl just starts to precipitate out is equals to option number A, 2 × 10⁻⁷ molar. Okay, what you actually find out that the molar concentration of iodide ion has been reduced from 0.05 to 2 × 10⁻⁷ molar. Is it okay? Fine. Option number A is the right answer to this particular question. The question over here is, which of the following is not correctly matched with respect to the intermolecular forces existing amongst the molecules? Okay, fine. Which of the following is not correctly matched with respect to intermolecular forces existing amongst the molecules? Option A, benzene is having London dispersion forces. H3PO4 orthophosphoric acid is having London dispersion force plus hydrogen bonding. HCl, it is having London dispersion force, dipole-dipole attraction. D, ICl, London dispersion force and hydrogen bonding. So which one is not correctly matched? Remember, all the molecules, they do have London dispersion forces. Why? Because of polarizable electron cloud. So whether a molecule is a non-polar molecule or a polar molecule, it will do have London dispersion force because of polarizable electron cloud. To London dispersion force, we also say it as instantaneous dipole-dipole attraction basically. At any instant, a dipole has been generated. At any instant, dipole is actually generated in non-polar molecule. So we actually say it as instantaneous dipole-dipole attraction also. Okay. So if I talk about statement A, benzene, it is a non-polar molecule. So it will do have London dispersion force. Absolutely right. It will have only London dispersion force. Option number A is actually right. I mean to say it's correctly matched. Talking about H3PO4, phosphoric acid. So it's P double bond O, OH, OH and OH over here. Absolutely right. Yeah, of course. Along with London dispersion force, this orthophosphoric acid, it too have hydrogen bonding. The molecules which have OH bond, NH bond, FH bond, they do have hydrogen bonding. Are you getting this particular point? So along with London dispersion force, they do have hydrogen bonding also. Okay, they'll form hydrogen bonding. Oh, absolutely right. So B is also correctly matched. Talking about HCl, it's a polar molecule. Okay, so polar molecule do have dipole-dipole attraction in addition to London dispersion force. Why? Because see, if I just talk about HCl, okay, it's delta positive, delta negative. Dipole-dipole attraction is there or not? Just have a look. If I just talk about, this is HCl delta positive and it's delta negative. Dipole-dipole attraction forces are there. Okay, so HCl along with London dispersion force, it do have dipole-dipole attraction. C is also correctly matched. If I talk about ICl, yeah, it is a polar molecule. No doubt it is a polar molecule. It's I having delta positive charge and it's chlorine having delta negative charge. But it actually have hydrogen bonding. I don't feel like that it is having hydrogen bonding. No, there is no hydrogen bonding over here. There is no hydrogen bonding over here. Rather, we can say that over here it has hydrogen bonding. Okay, so dipole-dipole attraction is there. London dispersion force is there. And yeah, we can say that in the molecules where we actually find what? OH bond, okay, NH bond, okay, FH bond, they do have hydrogen bonding. So in HCl, we cannot say that it is having hydrogen bond because we want the molecules having OH bond, NH bond, okay, and FH bond. Okay, so they will be having hydrogen bonding. So H3PO4 basically I want to say, it is orthophosphoric acid. It is having hydrogen bonding along with London dispersion force. HCl do not have any OH, NH, FH bond. So it will have only dipole-dipole attraction as well as London dispersion force. Talking about ICl being polar, it is actually having London dispersion force. But being polar, it will have dipole-dipole attraction, not any hydrogen bonding. Option number D is the right actually apt answer. Option number D is the right statement you can say or right answer you can say for this particular question, which is not correctly matched. The question over here is by which reagent the alkyne converts to cis-alkene? Purely cis-alkene? Yes, purely cis-alkene. So, it's only the Lindlar's catalyst. It's only the Lindlar's catalyst in the presence of whom cis-alkynes are basically partially reduced to purely cis-alkene. The addition of hydrogen substituent always proceeds via syn addition. That means the addition of substituent will take place on the same side of the double bond. So Lindlar's catalyst is hydrogen, addition of hydrogen. Okay, in the presence of palladium BaSO4. This is actually Lindlar's catalyst basically. If I talk about option number A over here, it's Cr2O3 supported over alumina. It's actually the reagent which is actually used in the process of aromatization. Okay, H2, addition of hydrogen in the presence of palladium BaSO4. It's the Lindlar's catalyst basically. Okay, Lindlar's catalyst. If I talk about sodium in presence of dry ether, it's the Wood's reaction basically taking place. Okay, alkyl halide, when they are treated with sodium in presence of dry ether, we actually form the corresponding alkane to it, the higher alkane basically. Sodium in presence of liquid ammonia, it's Birch reduction, which actually give us purely trans alkene. So this particular reagent is going to give us trans alkene. It's only option number B, the right answer to this question. So if I just add hydrogen in presence of palladium BaSO4, we are going to get the cis-alkene basically. We are going to get the cis-alkene basically, wherein there is the addition of hydrogen on the same side of the bond. Option number B is the right answer to this question.